In this part of the video, I would like to explain about the sensitivity and specificity. Medical tests are characterized by two features, sensitivity and specificity. Sensitivity refers to how accurately a test identifies people disease who have disease or true positive. Specificity refers to how accurately a test identifies people who do not have the disease or true negatives. These terms are best defined by an example. Suppose the 10 women undergo a test to detect cancer and 3 of these women have the cancer. If the test accurately detects all the 3 cancers and does not incorrectly flags any of the normal individuals, then it has both high sensitivity and specificity. If the same test detected all 3 cancers but also incorrectly identifies 3 normal samples as cancerous or false positive, it would have high sensitivity but reduced specificity. If the test accurately detected only one of the 3 cancer cases, it will have reduced sensitivity. This presentation takes a look at audio spectroscopy. Audio electron spectroscopy, abbreviated AES, is a method used to determine the composition as well as surface layer of a certain sample. It is completed in 3 steps chosen in the following slides. Step 1 is involved the ionizations of a core electron. The red arrow signifies the energy of the sample. The tan sphere corresponds to the electrons at the core of the shell, and the blue spheres goes with the electrons on the outer shells. The atom is ionized by removing one core electron. In step 2, it begins when the upper level electrons falls into the lower level of electrons by releasing a quantum of energy. In step 3 of audio spectroscopy, the energy that is released from the second electron will excite the object electron that leaves the atom. Once the object electron leaves the atom, it is then run through the spectroscopy and analyzed. The instrumentation of object electron spectroscopy is shown in the part with this diagram. The sample is running through the spectroscopy and is usually a solid compound. The sample moves through an electron gun/optical ion source. It is comprised of an ion beam that sputters in the sample surface. The electron analyzer is usually a cylindrical mirror analyzer. The detector consists of an electron multiplier, which consists of diodes that are connected to a resistor. Second electrons are produced in these steps. The data is processed by displaying different bits of certain of each surface. This slide shows some advantages and disadvantages of object electron spectroscopy. The first advantage is that an AES is becoming simpler to use. The analyzer have high sensitivity when chemical analyzers are run.
Photoelectron spectroscopy, or PES, is some evidence to help show that electrons exist in orbital from lower energy closer to the nucleus to higher energies further out from the nucleus, and also that different orbital have different energies. UPS and XPS, where UPS stands for ultraviolet photoelectron spectroscopy and XPS is X-ray photoelectron spectroscopy. UV light is energetic enough to eject valence electrons from the surface of active metal. X-ray have enough energy to eject electrons within an atom if they have enough energy. So in XPS, the difference here is high energy X-ray are coming in and they can actually eject electron from anywhere in an atom. Imagine your ultraviolet light is coming in and hit a core electron. If it has enough energy, shown on the right, it can actually eject the electron and knock it out of the electron. Binding energy is the ionization energy it takes to remove the electron from ultraviolet light that has more than that energy, and the difference between the binding energy and ultraviolet light is the kinetic energy that the electron leaves and be measured. The ultraviolet light's wavelength and energy is known, then the difference between these two gives the binding energy of each electron. Here is the diagram showing the energy of the photon coming in as an equal H nucleus. Those single wavelength X-rays come in and eject electrons from an atom, and those electrons zing out with a kinetic energy equal to 1/2 mv squared. And again, the ionization energy is just the difference between the energy of the photon coming in and the kinetic energy of the electrons as they are leaving. Here is a diagram of the device for measuring energy of the electrons coming out. Photon on the left with X-ray beams coming high energy photons strike a solid surface in a vacuum. Electrons then come out and go into a detector following a circular path established by electromagnet. Then they are caught by a detector which then determines the number of electrons at a given magnet. Here is another view of the device in a different diagram. The detector then converts this into an electrical signal and then turns it into a spectrum that then has to be interpreted. Our high energy X-ray photon can come in and knock off an inner core of electron. It takes to knock the electron, the less energy of electron has in terms of kinetic energy. A pair of atoms joined by a covalent bond can be thought of as being light balls on the end of a vibrating spring. The bond can vibrate with different amount of energy at a frequency that depends on the masses of atom and the strength of the bond. Lighter atoms give higher frequency and heavier atoms are more slowly and so give lower frequency. Stronger bonds give higher frequencies and weaker bonds lower one at room temperature. Most bonds will vibrate with lowest possible amount of energy, but if radiation of a right frequency is supplied, the bond can absorb energy and vibrate with greater amplitude. Most bonds absorb energy in the infrared region of the electromagnetic spectrum, which correspond to heat. Raman spectroscopy is based on the scattering of light by molecules. Each molecule has different ways of I-beam and this change depending on its shape. These are associated with particular energy levels. The molecule can only exist long-term in one of these set modes. Here we have a methylene group which are 6 different vibrational modes, which it can occupy when light interacts with the molecules. The molecule can receive energy from an incoming packet of energy known as a photon, which promotes it to a higher energy. If this does not match one of the modes of the molecule, it immediately goes back down to release a photon. Here, one of 3 things can happen. In the majority of cases, the molecule relaxes back to its original vibrational energy state. which is known as elastic scattering, but 1 in every million scattering event is inelastic. This means that the molecule spontaneously relax to a vibrational energy state, which is higher or lower than the original state. By measuring the difference in energy of outgoing compared to the incoming photon, the energy levels of the molecule can be determined. The energy level also are unique to each molecule, and so they are act as a fingerprint allowing the molecules in a sample to be determined.
In this slide, we are going to talk about secondary ion mass spectroscopy, in short, SIMS. For the basic working principle, first, the fire energetic ion at a solid act as a primary ions. The solid that emits or sputtered are positive ion, negative ion, electron ion, and neutral ions. So these secondary ions produce a mass spectrum. For the introduction, the technique of secondary ion mass spectrometry, or SIM, is the most sensitive of all the commonly employed surface analytical technique. It is capable of detecting impurity elements present in the surface layer at parts per million concentration and bulk concentration of impurity of around 1 parts per billion in favorable cases. This is because of the inherent high sensitivity associated with the mass spectrometric-based technique. There are a number of different variants of the technique. First, static SIMs that used for sub-monolayer elemental analysis. Second, dynamic SIM used for obtaining compositional information as a function of depth below the surface. And the last one, imaging SIM, used for specially resolved elemental cases. In SIMS, the surface of the sample is subjected to bombardment by high-energy ion. This leads to the ejection or sputtering of both neutral and charged positive or negative species from the surface. The ejected species may include atom clusters of atoms and molecule fragments. In traditional SIMS, it is only the positive ions that are mass analyzed. This is primarily for practical ease, but it does not lead to problems with quantifying the composition data, since the positive ions are but a small, non-representative fraction of a total sputtered species. The displaced ions have to be efficiently extracted from the sample region and subject to energy filtering before they are mass analyzed, so that only ions with kinetic energy within a limited range are mass analyzed. For SIMS of imaging and depth profiling, there are two applications. First, surface imaging using SIMS and SIMS depth profiling. The aim of the measurement is to obtain conventional image of the surface from the secondary ion spectrum with minimum possible damage to the surface. And then the main problem is to ensure that sufficient signal is obtained at the desired spatial resolution whilst minimizing the ion flux incident on any part of the surface. So the surface imaging using SIM is the most easily achieved by switching from the traditional instrumental approach of using continuous flux ion guns and quadruple mass spectrometer detector. To use pulse ion sources and time-of-flight mass spectrometers, the TOF are much more efficient way of acquiring spectral data and also provide a good resolution and sensitivity up to very high masses. Using such instruments like SIMS with a spatial resolution of better than 50 nanometer are obtainable. For the SIM depth profiling, the aim is to obtain information on the variation of composition with that below the inertial surface. So it's obviously particularly useful for the analysis of layered structures such as those produced in the semiconductor industry. Since the seam technique itself relied upon the removal of atom from the surface, it is very nature destructive technique but also ideally suited for depth profile application. Thus, the depth profile of a sample may be obtained simply by recording single seam spectra as the surface is gradually eroded away by the incident ion beam probe. A plot of intensity of a given mass signal as a function of time is direct reflection of the variation of its appearance or concentration with that below the surface. One of the main advantages that seems offered it is sensitivity to very low sub-parts per million or parts per billion concentration of elements. Again, this is particularly important in the semiconductor industry where dopants are often present in a very low concentration. Thank you.